Good morning, Shito.
Good morning, sir. Good morning, everyone present in this online platform. Today, we are going to organize our third webinar of the webinar series of VLSI and microelectronics. Today, we have with us our ex-student, Mr. Rohit Kumar Thakur. And now I am asking our director, sir, respected director, sir, Dr. P.K. Manna, sir, to inaugurate our session. Over to you, sir.
Sorry. Hello. Am I audible now?
Yes, sir. You are
Oh,
audible
it was
now.
actually it was muted at that time. Very sorry. So, good morning, Mr. Rohit Thakur, and it is a matter of great pleasure to inaugurate such session where our own students is a big speaker, and we feel proud of you. You know the ins and outs of our institutions. You have gathered sufficient knowledge after our institutions from NIT Patna, where you did your PG courses, and hopefully, I am sure that you will share your knowledge, your expertise, who ultimately it will motivate our present students, your younger brothers. So let us start without wasting any time. I like to start this session. Mr. Rohit, hello, Mr.
Yeah,
Rohit,
yes, sir.
can you
Thank
hear
you.
me?
Yes, now I can hear you.
So comfortably, you share your knowledge, you motivate our existing students, present students,
Mhm.
and such that they can gather some knowledge and inspire to motivate themselves. Thank you. Please start the session.
Yeah, thank you, everyone. Thank you, sir, for such a wonderful introduction, and also Sutapa ma'am. Like it's good. Like I'm feeling itself like happy to that I got opportunity to tell and present something here. So I'm just starting now. Please let me know when my screen is visible. I'm sharing my screen.
Hello, Brijesh Kumar Jadhav. Please mute yourself. Brijesh Kumar Jadhav.
My screen is visible to all.
Yes, yes, it is visible.
So today, I'm gonna start discussion about the RTL to GDS flow. Basically, this is the chip manufacturing flow, what the ASIC design flow used in the industry. So it is semi-custom design that we usually call. So RTL, we write the transistor level logic, and GDS is the final layout for any chip that is go in the fab lab for the manufacturing. So the content will be IP, that is the intellectual property, each library, each block, then CAD views, the view related to those IP, then classification of those views, then how the flow works, how IP from scratch is started. We write the code for that, then it go for the final layout, and then go to the fab for the fabrication. Then library development flow, there are a lot of methodology we use to develop those library, lot of type of model, that electrical model, behavioral model we have to use while developing a single IP library. So that we will discuss here. Then the methodology. So before going for the development, we have to finalize some methodology for any kind of flow. What will be the standard methodology for defining that with different technology. So as you know, technologies are changing every day. So methodology changes with the techno, and on the basis of that, we develop the library. Then we have to validate the data, what we are providing or what we are generating is proper or not. It is working functionally proper, or everything means it is working as according to the specification or not. That we have to check. Then result, conclusion, and references. So first of all, it is good to make this webinar interactive. If you have any doubt, any questions in while discussing time, you can ask me. So it will be more interactive, so more understandable to all of you. So first of all, IP, what we call IP. Basically, a simple full adder, if we are designing, that is also a IP. That is also a sub block. So we can call as a IP. So there are different kind of blocks, different kind of library we use in our chip in SoC. So first we develop those sub block. Then we go for the SoC by combining those SoC, and finally we have chip, which is like processor, whatever you are saying, processor or any kind of clock generator, different type of chip we use in our daily life. And CAD view is basically the representation of those IP in the soft form. So like if there is a full adder, we have first there the schematic view, then we have their layout view, then we go for the timing, electrical specification of that IP, then those create a soft copy of that library, and then we integrate those IP for a specific function that we call SoC, system on chip, and that is the functional final chip that we make. So classification of CAD view, if we say classification of CAD view means like if we are saying about any chip, if we are talking about any IP, it has mainly the three part. First is the front end part, then back end data, then binary database. Front end basically the behavioral specification or defining the top level where there is no information related to the techno. It is basically the specification related information we have, and we try to achieve the functionality. That is the front end part. In back end, we usually try to map those functional IP with some technology. You might hear about 90 nanometer, 65 nanometer, 40 nanometer, 12, 22, 4 and 3 nanometer, 4 nanometer. So those depends on the backend on which techno we are mapping same functionality. So if we are mapping the same techno on same functionality on 4 nanometer, 3 nanometer, there will be huge differences. So those all will be comes in the backend if we are talking about any techno. And finally, those after completion of those IP, we create one final database, that is the GDS form, which is a binary database. It go to the foundry for fabrication process. So let's start with like very basic, that we have the logic gate. We all know about all the basic logic gate, that is AND or XOR, their buffer, NAND gate, NOR gate, XNOR, NOT gate. So these are the basic means gate which we use to implement a specific function that we want. So before we go to the like, let's take example of AND gate. So functionality of AND gate, that is like you can see here 0, 0, 1. So we know like the AND gate is there and its functionality, it has specific functionality. Similar for different gate, it has different functionality. So like you can see all logic gate truth table is there. So truth table basically it defines how our gate is going to work. If it is not gate, it will invert our input. If it is NAND, its function will be like according to this truth table. Similar for exclusive or an AND gate. So now this is like top level digital design. We have to map any functionality using these gates. Then it comes to the transistor level. So usually right now we are in the edge like advanced technology, right? So 3 nanometer, 3 nanometer, 5 nanometer, 9 nanometer, we all are working, right? So on those basically we use mostly MOSFET for our like any chip designing. So there's NMOS, PMOS. So these are the like symbols of NMOS and PMOS, how we define it. Similar way, if you see, there are different way of defining the MOSFET. It depends on like what type of circuit you are making. If you are a like analog engineer, so if you are designing any analog sub block, you go for the current. Usually, you like look for the current, how current is flowing in your circuit. So you can see here, like we are defining here arrow. So NMOS basically drain to source current is following. So you can see here. So it defined by the arrow. This type of notation mostly used by the analog design engineer. And if you see here, same thing is here. This is PMOS, this is NMOS, and it is noted by some not. You can see here. So this is PMOS. This one is NMOS, and this is used by the digital design engineers. So same thing with different kind of application we define in different way. So basically, what is the MOSFET? If we are talking in the digital design, it is just a switch. We call it as a switch. If we are talking in the analog, it has huge different voltage level, current. We have to deal with a lot of things, lot of characteristic, complete characteristic of a like how electric field is behaving, how current is flowing, how voltage sensitivity is. So but in digital we have to like more care about the switching behavior, how it is like switching. So switch can be two types. So one is maybe the series and other one is the parallel switch. So if you can see the first one, if both switch is enabled, then only this circuit will work. And this circuit will work when any one of switches. So it is also defining the basic gate only. So if anyone can tell me like which type of gate it is. Next, yeah, uh, logic. So we implement those digital gates we using the transistor level. So you can see here like this is the NAND gate. NAND gate is defined by here transistors. So PMOS, NMOS are connected here. If these logics are, see, PMOS usually it's called a strong one. It usually it's used for taking 0 to 1, and NMOS is usually used for the discharging the circuit. So if you are putting at x0, let's see, we are putting at x0. So the PMOS is active low device. So if you are putting 0 at gate, so first of all, a transistor has 3 terminals. One is source, drain, and gate. So here it is source, drain, and gate. For NMOS, it is drain, source, and gate. So when we give some voltage on the gate, current start to flow from drain to source or source to drain based on the NMOS or PMOS. So depending on the inputs what we are providing here, output will be come out. So this is basically the transistor level of NAND gate. Same, it is the transistor level circuit of NOR gate. So that is the basic of any design that we have to know. First we have gate level, then we have these all are finally going to map with the transistor only, and finally this will be the schematic, and after that this schematic we will make the layout, and which will make our final GTS database. So we will go one by one each flow where how it is going to be used. So first, hardware descriptive language. So there are three type of language usually we use: Verilog, VSDL, and system Verilog. So Verilog is mostly used in the industry. VSDL sometimes we use for some special kind of IP where it needed, uh, and system Verilog we use for the verification of that block. So if you can see, like let's see, it's a AND gate. So we have to define this AND gate. This is the truth table. So how to define this truth table using the Verilog. Verilog is similar like C, C++. It's also a hardware. It is a kind of hardware descriptive language. So we used to define the UDP. UDP is basically the user-defined primitive. So we define UDP as well, and in some simulator you will get uh, already installed some syntax. Like if you are using AND gate, so there is a AND symbol you can see here. By using direct AND symbol, its simulator will work and simulate it. So based on the modeling what we are using, so basically there are four types of modeling we use: behavioral, structural, then data flow, and one is the switch level modeling. So first one is like if we are talking about the behavioral modeling. So behavioral modeling, basically we used to write the behavior of any circuit, how it is going to look. Based on the specification, we write anything. We don't care about the what are the resources we have. But when we are talking about the structural modeling, we have to take care about what are the resources we have, is what are the gates, logic gate, or what are the standard cell library we have, what are the sub block, like which type of flops we have. So based on that, we write the structural. In data flow, it is similar like writing the equation that we used to write. In If we are writing any expression, so if by equation, those we define using the data flow. And in switch level, that is very low level designing. So we define we have already seen this is the switch level design. This we can call as a switch level design as well. So this is the defining the AND gate, how it will look. So we can define using primitive as well, or we can use some syntax as well, depending on the simulator what we are using. So as like AND gate, we can define any type of function through the behavioral modeling in Verilog. So you can see like here we have tried to implement some muxes, or how it will work, or like how input is coming and how output will go. So we are trying to find we are trying to define here some functionality. So not of A, not of B into not of C. And so those things we can define here directly. So you can see it is like we are calling here NOT gate, AND gate. So this is basically a structural level design. So you can see here there are some inputs, some output. First input we are putting in gates, and then we have done the NOT or operation on this output. Let's see this we are take one example that we are making one clock generator. Is a clock generator, which clock generator block which can make clock of any duty cycle. So basically, a clock has usually, if you see a clock, how it looks, so it has 50% duty cycle. We usually see in one period, half portion is high, half portion it is low. Then we call it as a 50% duty cycle. But like in real testing, we make different kind of clock. So here I have defined a very basic clock generator, where you can see like we are defining the clock cycle, complete clock. We are generating with a clock with different kind of duty cycle. So in clock, we can say we have two part. One is the how it will work. So if you see a circuit, there are some circuit which is working on the positive edge, some are working in the negative edge of the clock, and some are working on the latches are working usually on the high level and low level of the clock. So if you see here, we are defining clock out, clock counting. Here, based on the this is our input clock. So this is our main input clock which we are providing here, through which we are generating the clock of our choice. So what will be its duty cycle and anything. So we are using here one flag count, so which will keep the track of how much positive is already spent. So based on that, we are writing that key. Let's see, our clock has period of 16, and we want key for first after fourth clock, uh, it should high for two or three clocks, and then it should low. So based on that, if we provide input on the first high cycle number, that is 4, and then how many high cycle we want, so 3 4, so it will work and it will generate the clock according to our input. So as we are providing input, based on that it will generate the different kind of duty cycle. So when you simulate that circuit, then it will you can see this way. So whatever the functionality we have written here, plus, minus, or greater than, lower than, so those things are implemented through simulator. And you can see here, those blocks are implemented here. So based on that, simulator read those code and it try to implement those function. And this is the behavioral view of that. So block level behavioral view. So you can see here some muxes are there, some uh, adder, subtractor, multiplier, comparator, some gates are there. So it's calculating on the base of simulator only. So it can create more latches, so you can enhance this view as well based on your coding. By improving your coding, you can enhance this behavioral view as well. Now our circuit is prepared, but like how to verify it? So to verify this model, we have to write some code where we give some input, random input, what we wanted to test, and it will give output based on what we are providing at input. So that is called test bench. So we usually write the test bench to verify our circuit. So for verifying this clock, what we can do, like we can provide some, let's see, we are providing here clock cycle length. It should be the length of 16 cycle. Then first high cycle is 1 and then 4. So it means like out of 16 clock, it will be high for the first 4 cycle, and then for rest it will be the 0. So we can say like for first 4 out of 16, first 4 it will be high and rest will be 0. The duty cycle of this clock will be 1/4. That is the 25%. So how we define those? So we are calling, you can see here, clock gen main we are defining here. We are calling that that main module here as a sub module, and then we are porting them, port mapping them with the our test bench, and then we are providing some input through the test bench in the main circuit and seeing its functionality is proper or not. So you can see how it will look like. This is our test bench block, this is our main block, and this is our clock generator. So from clock we are giving the main clock, and then based on what input we are writing in the test bench, it is directly getting fit to the our main clock generator circuit, and we are getting the desired output at the output port of what we which type of clock we want, of what duty cycle. You can see here functionality as well. So these are this is a small clock, main clock that we are providing here, and out of this we are generating a clock with high duty cycle or low duty cycle as per our requirement. So as we have given there key for 4, after 4 it should be high, so it is high. After each 4 clock it will be high, and low for the rest of the clock. So this is a waveform diagram of same circuit. So first means there are three. If we talk about the RTL behavior, first we write the code, then we go for its behavioral view, how it is looking. Then we check, like if we have extra latches or anything that is not required, we can remove it from our code and again see the behavioral view. And then we go for the functional verification. We write the test bench, we give some input to our main sub block, it will look like this, and then we get the output. We check the waveform of the output as well as input, so it is working accordingly. So then we can say like our circuit is functionally correct. After this up to this part we can call it as a front end, because we are not caring about any technology, anything, any resources. We are just caring about the functionality, what is given in the specification, it is achieving or not. Then we have to map this functional functional block through the some technology. So that is the next part, that is called synthesis. From synthesis we can say we are starting the backend. We can call from synthesis backend started, because here we are talking about the technology, which type of techno. So it depends on the customer requirement. If they are saying 3 nanometer, 5 nanometer, or whatever means whatever their requirement, on the basis of that we first create the standard cell library. Standard cell library means like the AND gate, NOR gate, all type of latches, flops, those we optimize on the. We used to do the full custom design for the standard cell, then we make their library and we use those library in our main design for making SoC. So synthesis, basically it read the code, then it translate the code and check whether our code is synthesizable or not. So based on what are the resources we have, it check if those resources are not we have. So we have to use the other structural way, how we can achieve with the whatever gates or whatever the resources we have. On the basis of that, we have to create our our code, and then we map it to the structural level, then we target to the technology. So basically synthesis is translation from code to the gate level, then optimization, what means whichever unnecessary latches, blocks are coming in the design, we have to remove that, and then finally mapping those with the our already created standard cell library. So what are the input that we used to provide? So first library, which is basically standard cell library, then RTL code of SoC. Then we have to write some script, because we use different type of, there are different type of synthesis tool, design compiler. Other than this, design compiler is basically from Synopsys, so we are using design compiler. So, and some script, and there is some constant we have to write regarding the design. Means constant, if we are saying, we can say what will be the fan out of the design, what will be the maximum transition, maximum load, maximum area, power consumption. We can control these all things while checking whether we are achieving proper PPA or not. PPA means power, performance, and area. So for any circuit, if we are making any SoC, we have to care about PPA. So how this PPA is like, but there is always trade-off between these three. If you are trying to achieve good performance, area will, you have to like area will increase, or sometimes power also increases. So we have to write a proper way constant file, then script for controlling these all inputs to the, like we have to set different type of variable in the tool itself. So there are different tool variable we have to control. So for that we write the tickle script, and then basically finally the wire load model we have to use. So wire load model basically, you are seeing there are some connectivity, port connectivity here in design itself. So this connectivity should it has some parasitics. Parasitics means like it has some resistance, capacitance, and inductance while connecting. So these parasitics has also impact on the delay. So we have to model it as well. So based on technology, we have different kind of wire load model that we call wire load model, that help us to estimate the delay of the nets, whatever the connectivity between the two port, those delay we used to estimate through the wire load model. Then we provide these all input in the design compiler, and we get the final net list. So how synthesis starts? So RTL development. So synthesis is a major role, we can say, like it is only the first part of backend where we we try to achieve the complete PPA specification what customer has given. So on the basis of that, we analyze which type of library we have to use, and then we code accordingly, and then map it to the technology. So RTL development, then we do the partitioning at RTL level. Then constant we write, what are the constant of the design should be constant. I already told that is fan out, area, power, and transition, how much transition, input transition. So those things, clock MPW, clock minimum pulse width, what should be there. Those things we control through the constant file. Then we check those constant. Then we do the translation of code into the uh, gates. Then we do the logical optimization on those gates through boolean, whatever boolean expression we have, using Karnaugh map. And there are different type of methodology we use to minimize those boolean expression, and then it finally map to the technology. So it's basically a cycle, you can see. Like first we are taking library, writing the code, we are changing code to the gate level, then we are checking through all parasitic delay are proper or not. If it is passing, we have the proper netlist. Otherwise, we again go for the optimization, remapping. Maybe remapping of cell can work, or uh, different kind of. If we are using, let's see, we are using two buffer is coming in a path. So on the place of that, if we are using one big buffer, delay will be less. So on the basis of that, we do some changes in our code continuously, and then finally we optimize our netlist, and that will be our final netlist, gate level netlist. So what are the outputs we will get from the after synthesis? So before synthesis, we have RTL code only, and which is functionally correct. Then after synthesis, we have mapped gate level netlist. Those RTL code what we have written is now we have in the gate level form, what library we have given as an input. Then we have complete timing of the circuit, power of the circuit, and the some constant what we have set there for analysis. So you can see here, so our behavioral level was looking like this one is our behavioral level, where we cannot understand where the gates and what gates it is using. There are some blocks it is creating at it's in some comparator and something. But now these finally blocks are changed by the actual gates. So in digital, everything is gate only. So it's now converting in the NOR gate, AND gate, or some latches, some flops based on the function. So this is completely the gate level netlist of the same circuit, and it is mapped to some technology. So you can see here, here we are. You can see this is with 28 nanometer FDSOI. There is some different kind of technologies there. So it is basically a 28 FDSOI. With 28 FDSOI, it is mapped. So our gate level netlist is look like this. So where you can see this is our submodule block, and we are mapping it through the main port. So after this gate level netlist, we check the timing is proper or not. So basically, you can see here whatever the timing is there. We are getting here complete path timing. What is the data arrival time? What's the clock time? Everything we will get in this timing report. Then we have power report as well for the same circuit, how much power it is taking. So basically, if you talk about a circuit, it has mainly two type of power. One is the static and other is the dynamic power. In case of static power, we mostly call about the leakage power. Leakage power, it means like when our circuit is in off state or stable state, then how much current is taken from supply and it is going to our ground. So that time also power dissipated, so that power we call as a leakage power. Then in dynamic power we have two type of power. Basically, one is the switching power. Switching power is basically we have different kind of kappa node internal in the circuit, so they usually charge or discharge based on what input we are giving. So that is called the switching power. And one is the internal power. uh, so internal power is basically when our input state is fixed but out state is not changing on, but at that time we have some resistance for the MOSFET in the circuit as well. So those also dissipate the power. That is the internal power. So if we talk about the methodology how these power are calculating, so let's see if we are talking about the leakage power, how you will calculate the leakage power of any circuit. Let's see, we have and gate. Yeah. So if we want to calculate the leakage power for the circuit, we will put one load at the output, and then we will put some conditions here. Like we will take any one of the state, both are in zero case, and output Z is also Z is based on the input 0 0. It will be 1 or 0 based on that. So this is NAND gate. So if it is 0 0, then output will be 1, because these two paths are close, and it will start charging this kappa. So this will charge. On that time, we probe the supply, and we see, like, after charging, you will see two peaks. When we are giving some transition at input, it will charge our output, and then again it will go to the stable state. So we integrate that stable state. From there we will get the current charge, and then we multiply it with time and voltage. We will get the leakage power easily. If we talk about the switching power, how switching power is calculated, so like for charging or discharging kappa, it is half CV square. So based on that we calculate the switching power. And internal power, we again probe the supply and we charge the output, and then we see how much power is dissipated. Then we plot the complete current waveform we plot. Then in total power we minus the leakage power and the switching power, then we finally get the internal power. So these powers are calculated here for the complete circuit. You can see complete internal power of the circuit is 741 nanowatt, and switching power is 330 nanowatt. So total dynamic power is 1 microwatt, approx 1 microwatt, and cell leakage power is 39 microwatt. Then we have similar the area, like as we have optimized our gate and everything, we have some target for the chip area as well. How much area we can get for the this standard cell logic. So based on that, if you see like a number of ports, number of net, it is defining a number of cell, how many combination cells are used. So you will get complete data of those, and there as well as complete area. So total cell area, if you see, it is 71. So you can see here they have you can get partition of area as well, like where combinational logic is there, some are sequential logic, so and some are black boxes, means like uh, black boxes we can call as some macro which are fixed already, means those are full custom completely designed, we are not touching them, so those are black boxes. So here we are not using any black boxes, so that's why you can see only combinational and non-combinational uh, circuits are blocks are present here. Then design constraint, before synthesis I have said like we have to write some script and some constraint for any circuits, as like how much maximum transition, maximum fan out, maximum kappa, based on the techno, and maximum area will be the that we define in our the constraint file. So this file is very important, we have to write it properly to achieve the specification of the circuit. Then after gate level netlist, we have already gate level netlist. But we have already checked the functional through the behavioral view. So behavioral level netlist, we have behavioral level code we have written and we have checked it's functionally correct. But we don't know about the functionality correction of this gate level netlist. So how we can check? There's one more tool which is formality. Formality is what it do. It is basically check the logic equivalence. So logically, the code, two codes what we are providing there, it should be correct. So one is the gate level netlist that we get after the synthesis, and one what we have written in the RTL code, that is two type of Verilog code we have. So we feed both Verilog code in the formality tool, and then it do the equivalence, logic equivalence check, and finally it's reported whether it is correct or not. So you can see here like it check complete number of port are proper or not. So if it is matching properly, then it will print as a verification succeed. If there is any mismatch in the functionality or any port, it will report here, and based on that we have to again debug our circuit. So first one is reference. We take reference our main, which is the behavioral code, and then in implementation we keep our the gate level netlist what we get after the synthesis. So up to here we got idea about the netlist. Netlist basically means the Verilog code which we are getting is functionality correct and mapped to the some specific techno library. Then we go for the physical design. Physical design means like uh, we have to now floor plan properly, then routing, then we have to properly implementation. If we are talking about physical design, means implementing the chip into the real world. Means physically we are now we are placing the each block in the chip, and then we are checking whether it is the delay is less or not, area is less or not. So we have to optimize in the different way. So after getting SDC, that is design constant what we have set in the earlier, and the netlist, we import it. So there are some physical data we get in our standard cell library. Those are the left, basically library exchange format. This is you can say like if we have chess, if we are talking about, let's take an analogy, chessboard. So we have different blocks there. So each block has their area defined. Okay, this block has this side. So if we are defining different kind of rectangle, so different length and different width, so we first put those type of block in our placement, then we put our actual macro on those boxes. So we first create the site where we can place, and then we put the actual block on those sites. Similar way, these are lips we get the electrical specification of those standard cell which we are using in our circuit. Electrical specification means like what are the constraint of the design, means standard cell, that is our delay, that is our transition, how much sensitive our output with the input transition, then leakage power, internal power. This we usually define in our .lib. So different kind of data also present in the .lib, except the delay, leakage, power. We have some noise data, some current source model data. So they are different kind of modeling in the Liberty itself. Usually you can, if you see, there are NLM, NLDM, non-linear delay model, then the composite current source model. Composite current source model itself has a three type of model: timing model, it's a noise model, it's power model. So we use those data in our uh, uh, to analyze our SOC proper way in timing or power, it is proper or not. And we have technology file where we get the information about the PDK. PDK basically means like we can say about the how our chip is going to be fabricated. So those metal layer, those their thicknesses, how much thicknesses for those metal layer is defined, poly layer, and what will be their width. Uh, Based on the different kind of metal stack, we define the technology file. So in physical design, we have some flow as well. So first after importing design, we go for the floor planning. Then we are placing those blocks. Then after placement, we again optimize whether it is properly placed or not. So do placement optimization. Then we go for the clock tree synthesis. Then we connect the actual clock in our circuit and check whether the delay and everything is fine or not. Then again we go for their optimization. Then after routing, then we go for the actual means optimization of routing, and then actual routing we do. After that we do some noise analysis in the circuit, like if let's see if two nets are nearby, then if there is one aggressor, let's see there is some switching is happening on the aggressor, how it is impacting the victim net. Means if two net are in the parallel, if there's some switching happening the first net, how it is impacting the other net, if there's any bump is coming on that. So that also we have to analyze. Then finally, after final routing, we make the GDS data, and which is called as a tape out, and which go to the fab for the fabrication of the chip. So what are the setups we need for this physical design? First one is the gate level netlist that you have already seen. Then we have the left file. In left file, we can say left is the basically left data contain how it contain basically the coordinate of any block, all pins, and all the metal, only the metal coordinates. So how it is going to be mapped on the actual design. Then technology lab where we have PDK information. Then IO lab, IO basically the input output. So if we talk about any chip, it has two parts. One is the inner part, which is we call as a core, and outermost part is called as the input output. That is the IO part. So IO part is basically usually the big in size as compared to the core. Their voltage level also big. So we will talk about this thing also later. Then there is one pad frame file we needed where in what order we have to place the IO. So how it is going to connect to the external world, that we use to define the pad frame file. Those all padded coordinates. Then power pin and some corner and condition settings we need, like on what are the worst corner and the best corner for any circuit on which it will work based on the specification. So let's see, if you are talking, you can see here, this is like house plan. You can see, so in house we keep two washroom, stair portion. So then we are proper utilizing our complete home area key, where we can put our living room and all those things. So if we put it in a proper way, our complete area is uses and there is no wastage. So similar way in the chip also we have to think like there should not be wastage a single bit area also. So in that way we use different kind of algorithm. You can see here, let's see 1 2 3 4 5 blocks are there. So how we will place these blocks so that our area will be more optimized. So you can see same block is placed here in 4 way. So these two are seems more optimized as compared to this one. So these all things, they are different kind of algorithm, heuristic and other algorithm is also there. we use for the tool itself uses, and it gives some output estimation based on the input netlist. It give like what is the maximum optimized area we can get. So if you see this circuit, this is completely a chip inner look. So this is the inner part which we call as a core, and this is outer part which we call as a IO. So voltage level of core is very less. You can say it is 0.8, 0.9 volt, and the output it can be of, it is basically start from 1.2, 1.8, 2.5, 3.3, and more than that based on the requirement. Because if you see in the external world, there are huge noise. So if noise is more, we have to make our circuit more robust. So we cannot directly give 0.8 voltage to the outer world. Otherwise it will noise data will be added, and what we are trying to achieve, it will not get achieved. So we use the intermediate IO. So in IO there are itself, there are different block, driver, and then Smith trigger, some voltage level shifter. We shift the 0.8 voltage level to the same signal to the 1.2, 1.8 based on the requirement. So that our data, whatever is we are providing from core, is not get hampered. It will directly, without any noise, it get communicated to the outside world of the chip. So first in floor planning, what we do, we place our all the IO where we need to put our pad cells, where we have to put the corner cells, ground, supply, those all things we decide. Then we go for the, like in center area, first we do the power planning. Power planning means like we have common supply and ground. So first we make the rail for the power and supply. If you see here, the green color is completely the power rail we have created here. So that our all whatever the standard cell we will place here, it will connected to this nearby rail. So this we call rail in VLSI terminology. If you say, so power rails, we call power or supply rails basically, and these rails are connected to this directly pad. So after doing this power planning and power rail, we do the placement for our standard cell. So if you see now, the standard cell will look like this. These lines are the basically our power rails, and in middle of that standard cell are placed. So you can see there are number of standard cells. We cannot understood like which cells are there placed, but we can see how much area it is occupying. That is our the main motive. So on the basis of that, we set our constant and we get the area. Otherwise again we have to optimize that. After that, after doing the placement of standard cell, we go for the CTS. CTS means clock tree synthesis. Basically we are trying to put here the actual clock, and the clock is the most sensitive part of any chip, if you see. So if we talk about the basic of register, that is resistivity into length by area. So if you see, let's see, clock pin is here and then our block is here. So if we are trying to connect this loop block, so if their length is high, so if length is high, then resistivity will be more. If resistivity will be more, then delay will be more. So our circuit will become more slow. But we have to make our circuit more more speed, less power, less area. So where we can put our put, that first we decide, like, okay, if we put on this point, so it will be nearby to the all blocks where the delay will be less. So first optimization is this that we have to do. Then after deciding the clock pin, we go for the connectivity with the clock of the flops. So then based on that, the distance, let's see if some clock is reaching here, some clock is reaching here. So there may be difference between the clock path from here to here and here to here. So we have to make all switching in the same time or based on the path, because there is some output, which for this block maybe depends on this input. So if both are switching at the same time, we can miss some output from here. So we put some buffer, we can delay this path, so that after switching of this block, only this block will switch. So we do that also based on the path. And after finally we do the optimization. You can see, like, in the real world there's no ideal clock. We have some transition at input. So, and again, this transition is going to be increase with time. So because if you see this wire, if you put in a register level, RC level, so these are the parasitics of the wire. It will look like this, RC in this way. So this transition can changes from here to here. It may be more slow, or it may be happen that this clock is gone. So based, we have to decide the minimum width of the clock as well, and the connectivity path as well. So we are adding buffer here, you can see. So these are help to restore the clock. Then again, our if clock, whatever clock is coming from here, if it is like, let's see, up to coming, after coming here, it is getting degraded, but again we are putting buffer here, it will again restore. So regenerator, we can say these are blocks. So it can restore our the clock, and then it fit to the flops. So on the basis of that, we put different kind of buffer in our circuit. After placement, and clock tree, we go for the routing. Routing is like, you can see here some analogy I have did. So if there is a very less area, if you have very less area, and but you wanted different kind of connectivity at the same place, we do in our real life also. Some bridges, you can see multiple layer of bridges are there. Similar way used to do in our chip. So there are multiple layer on the base of how SOC is and how much big design it is. So sometimes if you talk about, let's see, inverter. So inverter has only one metal layer. There is no needed of any more connectivity. But if we are talking about any complex full adder design, so at least 6 metal layer is needed. If we are taking more eMMC, and there are different kind of IP, I2C, I3C, uh, different speed blocks, SerDes. So there we need at least 16, 17. So minimum there are 15, 16, 17 metal stack needed for the connectivity. If you see, this is chip level, how the connectivity is done. These are the gates, lower level gates. So we are connecting in different way with different layer. So if we have some connection from, let's say, M2 means like gate of, if we see the transistor, so these gates are main. These gates are connected through the metal layer. So these are main gate. So how this gate will be connected? If there are, let's say, 2-3 adder, 2-3 NAND gate is there. So there should be connectivity between this port to this port. So it cannot be possible in one layer itself. So we needed more layers to connect these all things. So we do the different kind of metal stacking. So different kind of metal stack we have based on the requirement and block, how much big block is. So that is routing. We do the routing in this way. So after doing routing, you can see in this way, like as these are very small in size, so you cannot see at the top level, but it will change the color after routing. It will look like this in tool itself. Then finally, what we do after doing routing, we change the we replace our we have given the input as a left, and left containing the box side. It's just basically the frame, you can say, which has already coordinates we have defined. So in those coordinate, actual layout of the design get placed when we are replacing left with the GDS. Of GDS, basically it is the layout format of the design. So if you see, this is layout format. So here actual devices are placed. These all are the layout and actual devices design which we have placed here. So these are the IOs, and this is basically core part where our standard cell is placed. So standard cell are very small in size. That's why we cannot see it clearly. So we have to, like, we zoom it and then we see it. They are very small in size. After doing this, now we have the physical level data as well, and we have first what we have done, we have the RTL code level data, then we have converted into the gate level data, gate level netlist, which is mapped to some specific technology. Then we have final go for the placement, routing, and then CTS. We did everything. We do the timing closure as well. Okay, STA analysis we do on that, static timing analysis, proper, all path are proper and proper or not, or working functionality correct or not. Then we go for the physical verification of those IP, whether the layout what is created, what we are getting is correct or not. So validation needed in every step. So in physical verification, we first take out the CDL, means basically circuit descriptive language, the netlist, and then we compare it with the layout. So that is called the LVS. LVS basically layout versus schematic. It compares whether whatever ports block which is defined in our schematic is same present in our layout or not. That it checks. So number of block, number of connectivity, number of ports, everything it compares. And second one is the DRC. So in DRC we check like the width, whatever we are plotting here. Let's say we are given some supply or some fillers we have put in our middle of that. So those are proper or not, means it is according to the fab or not. So what is DRC basically? Every fab with regards to the techno, they generate one deck. Deck is basically a rule, a set of rule where they define the physical information. Okay, so the width of metal stack, metal layer should be this micrometer, or there should be distance between the two pad pins should be 150 micrometer, or difference distance between the supply and the IO pin should be 100 micrometer. So we have to follow all those things. Otherwise, it will, because we after layout as well, we do some analysis on those layouts, so that during the fabrication, if there's some itching or something is done, other part is not get affected. So we keep the minimum distance between them. Then if you see SOC, it will look like this. Lower part, then different in metal stack, it is connected. All gate level connectivity is done in that way, and all nets are there. So this is basically 3D diagram of the same SOC, what we have written code. Now how these SOC now go for the fabrication. This database in the DB format. So again, then for fabrication there is again a process. So fabrication steps are there. That itself is a long part. So in top level, if I am talking, first we create the mask, then mask, on the basis of mask we put those chip photos on those masks, we etch them, then there are different steps there. So these masks are like basically whatever chip layout we have, we put in this our some frame through which we will put some light, and then it will get printed on that silicon wafer, and based on the technology, it will create that circuit in actual on the silicon wafer using different uh, methodology, etching, uh, filling. So if you see, this is wafer. You can see there are different silicon wafer. It is the upper cut part. So it is a big roll, and we cut the small disc size, different kind of different size of, you can say different size of wafer is present in the market based on the quality and demand. So we put different kind of wafer, and then these masks are created, and those are printed in this wafer, and they go for the further process for the chip fabrication. So these all things are done through a proper methodology. So that is the what we have done right now. Is first we have done RTL design, then we go for the logic synthesis, floor plan, placement routing, then we check DRC LVS, parasitic extraction we did, actual delay analysis we did, simulation. Then we put some testability as well, design for testability, some flops, scan chain we used to put in our circuit, so that after fabrication whether our chip is working proper or not. Maybe like sometimes it's happen, it get sorted to zero, or sorted to ground, or sorted to supply, or some nets are getting sorted. Those things also we need to check after the fabrication. So for that we also inserting some kind of scan chain, that is that methodology itself called DFT. Then we usually follow the DFM in our circuit, design for manufacturability. It means like we try to make our layout symmetric, so that while fabricating there will be very less issue, or while doing the perk or different type of analysis, it will be easier. So what we have seen there are some, first is the specification level we have seen, then we go for the front end view generation, then back end view generation. So, and then we drive the CAD views. So basically, first, like if we are developing one standard cell, we have used standard cell here, but it is also get developed somewhere, right? So for that standard cell, someone is developing standard cell, then it's generating all the back end view, front end view. It means like layout, GDS, schematic, uh, Verilog model of each uh, standard cell. So and left NDM, there are different kind of data, NDM, Milky Way data we used to generate, and then finally we use it in our the SOC, and then we have to validate those each block first, and then final after integration also we validate our complete SOC in each case. So if we define the complete cycle of the chip designing is 30, more than 30 maturity is there. So usually in industry, if you hear, they will say ki, okay, what is the means, what is the maturity level of this SOC or the IP which is going to develop. So first is the NLR is the specification new library request, basically NLR. So there we first, it comes the specification from the customer, what they wanted. Then it go for the specification level to the, some team used to define, okay, what are the best techno or best block that we can use it for achieving this specification. So up to that there is maturity 7. Then we go for the design phase. Design phase, after designing phase we go for the layout, so which is up to maturity 9. After designing layout, we go for the electrical characterization of those circuit, and then we electrical characterization, and also we have to define the different kind of view which we use during our the complete flow, like Verilog, or we can say left, def. So those data we need during the different tool uh, for different methodology. Then after the final GDS, we go for the silicon validation as well. So whatever we have seen right now, GDS data, these data are taken care, and then these are fit to a block. So again, they used to write the code for the any FPGA board, or then and the ASIC code, or they put this GDS data on those block and check actual functionality is proper or not. Then that is called the silicon validation. And then finally, after completion of silicon validation only, we call it as a, okay, this is the qualified library. It can be used in the any SoC. And if we are talking about SoC, yes, this SoC is working fine. So this is basically the flow of the IP maturity level. So if you talk about the what are the type of file that we generate with the IPs after layout, after the schematic and layout, there are some for functional checking, timing check, low power check, Verilog, STF is basically the .lib. .lib means synopsis technology file. It is also the standard technology file which is defined by the synopsis cell for defining the electrical characterization of any circuit. Then some capacitance, ultra power model, emulation. Similar for the synthesis, we have some checks and some file we use to generate. Floor planning, same left, pram, abstract. So this all depends on the what flow we are using. So different company uses their different kind of tool. Some uses cadence flow. Cadence company has itself complete tool. Some product company uses cadence as well as synopsis. So whatever is best for their chip or analysis based on their resources, they use the flow, different kind of tool flow. Now, what are the things that we need to check in an IP? The functionality is correct or not, timing performance is correct or not, or the layout is proper or not according to the our PDK deck. Then possible error, what can be the possible error? What we can face is the incompleteness. The maybe sometimes some part, some block get missed, or then that is incompleteness. Inconsistency, there are the different kind of view layout we are generating. We are generating schematic. We have the Verilog model. So they all should be consistent with each other. So we have to check the inconsistency check as well on those. Functional error, those all are functionally correct or not in all view. DRC violation according to the PDK, it is working, it is correct or not, all the layout is proper, distance is defined or not, or antenna data what we are providing there is correct or not, and accuracy, everything we have to check. So but validating these all things, yeah, itself is a big challenge. Consistency because all are in different format. GDS has itself is a data binary database format. Left has its different syntax. Lib has different syntax. CDL has different syntax. So we create some setup environment and then we check all together. So for that, we make some configuration file, some validation tool where we give these all input and then we check those. We put some kind of check at our end. Okay, these checks are needed here. Consistency check, pin consistency check, cell consistency check, area check, coordinates checks. So we define the checks there in the configuration file and we get the output based on that. So we are talking about .lib there. So in .lib itself, like there are different kind of model we use. So based on the techno, we use the model. Like if we are talking about 90 nanometer, 40, 60, 28 nanometer, yeah, it is okay to use the nonlinear delay model. Where like we are giving some voltage source as an input and we are checking the output, how it is transitioning from input with respect to output, and we put the delay trip point 50-50%. So how much time it is input is taking to charge from let's see, this is the what we are providing at input. So how much time it is taking from go to zero level to 50%. Similar we check at output and then we find the time between the input and output, that is the delay of that path of the circuit. But this NLDM modem is correct for the higher techno. But if we are shrinking to the lower techno, we are it changes. The methodology itself changes for calculating the delay. So CCS model is there. So where we know that voltage level are okay, fine, because we are taking the voltage level at 1.50% only. But if we have current data, so we are providing some current set of current input, nonlinear current at our input, and we are checking the same for the output. Then we can check how the output is sensitive to the current, so that it will give our accurate delay. Same, I was talking about the aggressor and victim. So there are two nets if nearby. So if there's some bump is the nearby interconnects, how it is going to affect the uh, other victims. So if there's some bump, it should be get cancelled when it is reaching to the our actual design. So we have to make our circuit robust, and also the it should not like affected by any external noise. Same we do for the power analysis as well. So after doing that, we have Verilog model, everything we have, get level netlist we have, but how to know like it is working fine or not? So what we do, we put our data, delay data, what we have calculated in the .lib, we put those delay data in our Verilog file. There's some specified block in our Verilog itself where we define those delay, and then we back annotate them and check with the actual delay. So we have in initial time when we are doing the functional check, that time we have care about the functionality of the circuit. We don't care about any delay, interconnect delay we have not defined anywhere. We just write the code and then we check, okay, with as we have written the code, it is working accordingly to that or not. But in actual real world, we have some interconnect delay as well as the cell delay as well. So we put those delay through .lib, and then again we integrate those delay in our Verilog code, and then check whether our circuit is with actual delay, actual net delay, it is working fine or not. That is called the back annotation flow. So if you see, like this is our example, this is our .lib. So this is our .lib. So in .lib, and this is our Verilog. In Verilog, we define one block like this, if else function and a specified block. And here we are defining the delay, what delay it is. So let's say in Liberty model, it is like some pin is there, and on based on the pin, there is some delay data given there. So you will get in STF file, which is standard delay format file, when you are combining Verilog as well as Liberty. So from Liberty, you will get one SDF file, which will give you a path. Okay, PDL B is some input, and this PD10 is my output. So its delay will be 0.95 and 0.943. So these two are, one is for worst and one is for best corner. So here in both cases it is similar. So based on that we see. Then we validate it through tool. So we check how it is proper integrating or not, the path are properly identified or not. If arc is not present, if it is not connecting proper, then it will give error. Now, other than this, we have to model some mismatches also. So if we are talking about the fabrication process itself, like fabrication process has like first we have wafer, then we go for the like masking, then etching, then again masking. Different kind of mask we do for different kind of masking we do for putting a circuit on the chip. So in that cases, if a chip is present in our center of vapor or it is present on the edge, there will be difference. Some chip will be fast, some chip will be slow. So those things also we need to model there. So there are different kind of model we used to do. So there are few factors. If we talk about, let's see, temperature, voltage, there are basically three factors. Process means, so if we are talking about process, it can be the fast, slow, then typical, that is the nominal. Then temperature may be like a same chip can work -40, we usually take -40 degrees C to 125 degrees C range. So it should work in -40 degrees C as well, and 125 degrees C temperatures and different voltage level. So we have to analyze our circuit on the all voltages level, all temperature, and different kind of the processes. So we cannot control this factor. So we have to give some margin to our delay circuit. Okay, if these factors are also coming, if it is making our circuit fast or slow. So let's see if we are talking about very simple thing. We have electrons. We know electrons are flowing in our circuit. So if we are increasing the temperature, so what will happen initially? If we are increasing the temperature, so our electron get energy and it start to move fast. So in initial stage, our electron will start to flow with very speed. So current will be more. So our delay will be decreases. But after a certain voltage level, that is we can call as a Curie temperature, that we call normal temperature usually. So if temperature is more than that, so electron will get more energy and then it will start to collide with each other. So again, if it start to collide, current will start to fall, and current will start to fall means our circuit will get more delay. So there some with increasing temperature, sometimes our circuit is becoming fast. Again, with increasing more temperature, it is becoming slow. So we have to take care about all the factor of the circuit. So there are two type of variation: global and local variation. Local variation, it can be happen same intra-die, and global variation inter-die, it can happen. So we have to model this one also. So these are the some processes: etching, lithography process, implementation, annealing, and diffusion. This all we do in during the fabrication of chip. So in basically etching, we how we are etching whatever we are printing on our circuit. We have seen, I have shown you one mask. So according to our layout, it get etched on our wafer. We do lithography there, then we implement those circuit. Then we have to like some doping we do. So silicon, how silicon has two type: one pure format, that is not useful for us. So we do some diffusion, we put some impurities in our silicon, and then and different, there are two kind of doping, n type, p type. So based on the requirement we do, and that is called diffusion process. So it is also not constant everywhere. If we are doing diffusion as well, or then we have to do annealing or different kind of process, so that it can be constant uh, in all surface, so that the circuit what we are implementing is proper. So let's see, this is idle mask what we have created. So we have created it through software, but in actual, if you see, when we are printing and we are etching it, it can be destroyed. So we have to model these all things as well. Similar for the similar for the like oxide. If we see the MOSFET structure, we have to, when we are printing this MOSFET itself, when etching, there will be some there's no ideality there. There will be some differences over here. So it will also impact our. So we have to keep modeling of these things as well. So we put what we put. We take the number of random variables. Random variables, we can say, like we have different parameter of different parameter for fabrication. So for fabricating any MOSFET, we have already the SPICE model, and SPICE model basically define the each parameter of MOSFET, how it is going to impact threshold voltage and different kind of width, everything. So we put number of samples for those, and put the one Gaussian curve for those, and whatever the in middle one, we take it as idle, and we put early or delayed based on the variation what we are seeing in the delay or in the power or leakage. So you can see similar to the timing report, we have some variation we can see here, and this is a sigma value, which is called standard deviation what we are getting from the actual delay. So we put this, at least this margin, to the our circuit in initial time only, so that after fabrication as well, our chip is not get failed. So these are the variation you can see. Different with output load and different transition with different voltage level, how it is working. So this comparison you can see here. Here just I try to compare the same circuit with different aging factor. So in one I have this one is working normal, this one is normal, and this one I have tried to put some stress on the circuit. So after 2 years, means we have some model for stressing our circuit. So if some circuit which is working right now is fine, after 3 year or 2 year or after 10 year, how it will work? It will not work similar way. So we put some stress on that devices or circuit as well to check how it will work with the time. So there are differences. You can see like there's some slightly, it was earlier 12. If you see for same point, it is 12 delay, but later it becomes more. So there are some changes happen with time as well. So we have to model everything in the first, so that our chip should work at least 5 to 10 years properly. So list of check what we do. There are some timing arc check. We do power check, timing versus power check, SDF condition check, Verilog check, back annotation we did, property attribute. So this type of check we do. There are multiple of checks that we do on our circuit before going for further process for certification whether that IP is working or not. So different kind of model we have as well for the timing. So we analyze on those comparison where comparison is required. We do the comparison, NLDM, CCS, noise, CCS, PLDF. So everything we do, leakage on power. So you can see here with check and runtime also there is some differences with IP. So some IPs are memory, some IPs are memory macro, maybe some adder, some ADC block, or some IPs are IO. So they all have different kind of properties. So we have to see their behavior with voltage, temperature, and process accordingly. So these are some checks we define and we see the report based on that. Then we after this all thing happen, we go for the test chip. So how this IP going to be tested? So we put those things means like if you see here test IP, how we can check. So temperature 1, temperature 2, we put this is a one temperature sensor. Let's say temperature sensor diode I have shown here. Here, how this is going to be calculated. How it's going to be calculated temperature of any circuit. So we put some current. You can see here. Let's see. We are calculating at temperature T1 VPAD. What is the voltage level? Same we are calculating at VPAD at temperature 2 VB, and then we are calculating the slope from this. We can easily calculate the slope from this. So if we know the value of slope, we can easily calculate with margin for other temperature also. So we already keep it model, so it can track the temperature of our circuit. So there are these checks are 10 checks we needed. All type of leaf features different. Their delay should not be negative. Sometimes it comes because let's see our transition is happening more at the input and load is very small, so it will charge very fast. So our methodology, we know NLDM is when input is going from 0 to 50%, same output is going from 0 to 50%, then we are subtracting both time and we are getting delay. But if you see when input is changing to 0 to 10% only, output is getting full charge, capacitor is getting full charge. In that case, what will happen? Leakage will come negative. So those all things we analyze in our circuit. We have to take care of everything. So conclusion, we can say different kind of view, different kind of validation methodology we use, different type of technology data required, which and checks we needed. So final, then after that only our final chip get created. So you all can like try to understood the RTL to GDS flow. So once you will get an idea about those things, how a chip is getting fabricated, that will help you to more thinking about the how design should be, how you can optimize your design. References. Thank you. I can take question now.
All participants are free to ask questions to our speakers.
Hi, Rohit.
Yeah, hello.
Hello.
Yeah, hello, sir.
Hello. Hi, Rohit.
Yeah, am I
Can you hear me?
Yeah, I can hear you.
Am I audible?
Yes,
Yeah.
yes.
First of all, very nice and knowledgeable presentation. So how are you doing in synopsis nowadays?
Yeah, great. Right now I'm working on very niche technology. If you talk about, I'm working on the 3 nanometer. La-
Okay.
Uh, and last few months back only, I have completed 4 nanometer project. So it was like more learning, more research on the I itself. When we are going for the lower techno, different kind of issue are coming. What we read in our colleges, that is the basic. But when we are doing the actual circuit implementation, designing, complete phase, it gave more idea, more exposure to the
So
itself
are you
circuit.
following the
So
idealistic
it's good.
nowadays? I mean the proper, the IEEE roadmap. Are you following that one?
Sorry, I can't hear you properly.
I
Can you
mean the
repeat
idealistic.
again? Sorry.
Yes,
Yes.
yes. Well, actually, I was telling that are you following the idealistic curve, the roadmap for semiconductor curve, or the
Yes. Yes.
IEEE, the specialized curve for semiconductors nowadays working on?
Yeah. These all are the proper methodology. Only we are developing. Then we are going through the implementation.
Okay. So I mean, basically, my question is to, I mean, one thing that basically I am working on nanostructure.
Uh-huh.
So can I in some way uh, interlink your technology to my any nanotube or any nanostructure or any kind of proper quantum well which I'm working on? Is that possible in any way?
Yes, quantum. You see, quantum well is like a good techno. You can use quantum dot for creating the standard cell library. So there's still because when I was in MTech, I have also done that type of analysis quantum well. So there are a lot of free simulator as well available. So through that, first you can implement one standard cell library using quantum well. Uh, Using quantum well
Mhm.
technology, you can develop the standard cell library, some basic library you can develop, and then try to implement some kind of the basic circuit, like any clock generator blocks or adder or some kind of ALU, and then we see the behavior of the circuit is proper or not. So that it will give more like quantum data. But at that time I was not finding that much difference between the quantum dot. We maybe the resources issue. I didn't get that time that much. But like it is good to explore. I think that is also the next future. Nanotube and
Okay.
those things.
Yeah, basically, I'm working on Silver ticket. So I was some kind of trying to get some kind of clock information with my device for any kind of to use it in any lower technology, lower memory device or something like that. That's why I was asking.
Noise is coming. I can't hear you properly. Sorry. I'm getting a lot of noise at
Yeah, yeah.
where.
Oh, yeah. Basically, okay, okay. No, basically, what I was trying is to make an a proper interconnect with a proper clock information with my device for a standard SRAM cell or basic normal low power SRAM cell. So that's why I was asking, because it is my third objective to make any standard cell for my device. That's why I asking that can it be interlinked?
Yes. I didn't get your question properly, but can you please write like exactly what thing is? You can write in the chat box so that I can read it because I'm getting a lot of noise. Sorry, sir. Can you please
Okay,
write
basically,
in the chat?
okay, I will talk with you later. Yeah, talk with you later. No. I'll talk with you later on. So because
Sure.
I guess my students will get some ideas. Students are having any kind of problems. I mean, any kind of questions for it. That's one
Hello,
on my
Rohit.
end. Okay, over to you, ma'am.
Hello, Rohit. I have some questions. Actually,
Yes.
it was really difficult for you to make time for giving such a speech, but you have. I know how much you are busy nowadays, but we have some questions from our end, as you are also our alumni. So I think you have that motivation to help our students in every way you can, I think. So I have some questions, and as it is being a recorded call, so those students who could not join due to the exam time, so they may be listen from our conversation later when they will get time, and they will listen how you have enriched ourselves. So what is the speech you have just delivered? That is very, very, very fantastic. Because starting from the very beginning, you have explained all the level of design process through which we can design a SOC. From starting from the VHDL code up to the placement, routing, how etching, and all the process that can be possible for designing a chip. But Rohit, I have one question from my end, is that what should be the starting point of learning of a student so that they can achieve not up to this type of expertise, because you have done this expertise when you have worked actually on hand. But what should be the starting point of a student so that they can get interest as well as they can cope up with the VLSI technology within a very short time? Can you get my question?
Yes, yes. So, initial level like VLSI, we cannot start with the Verilog itself. So first we have to understand the basic digital circuit gates during our college time. Only second year, third year, whoever second year, third year student, they have like golden opportunity right now. They can do they understand the gates, and from gates they can start uh, implementing some small blocks. Like if they are reading about blocks or those blocks, they can start to implement those blocks within the Verilog code itself. So that at least they will get idea about how digital circuit we can make different kind of blocks within that digital circuit. So after understanding of the circuit, understanding of the blocks, they can go for the coding, with RTL coding. Then RTL coding, there are different kind of resources on the lab there. Yeah, they can make some project based on that, some processor. Itself, I got some like FFT processor in my college. That is my first VLSI project that I did after that. FFT processor. So those kind of some projects are there already. So if they start to do those projects, so I can suggest go for first standard cell library development. So standard cell library development means go for like how in gates can be created using transistor and as well as two logics. How we are defining the value. Those two understanding if you have, you can design any big circuit. Then you have to clear understanding about the MOSFET, how MOSFET is created. So if you have basic of RC circuit, MOSFET, digital gates, then these are the flow that will help you to implement any circuit. Beginning, you can start with the understanding of MOSFET or other kind of devices and the gate and implementing the logic.
Okay, Rohit, thank you very much. I have another question. Actually, how do you relate EDA design with the chip designing process? Actually, I want to give you another input to this question. That is, actually we have in our syllabus, that is EDA part, the electronic design automation. But often students did not get the knowledge of EDA, rather they cannot map the knowledge of EDA properly to the VLSI design. So my question is that what will be how they can map the EDA to the VLSI design?
In actual, we know the VLSI design circuit are there, so we cannot make circuit. we need EDA for implementing those circuits. So if we are talking about chip design, EDA comes in the first from the first point only. If we are using a simulator as well, that is also the part of EDA only. So EDA and chip design both are connected because we are dealing with the very small techno. We are not doing the connectivity on the platform. If we are making the digital design, any chip design, we have to design in the EDA itself. EDA is a kind tool. The different companies have different tools they used to provide. So if we are doing a chip design and we are implementing those design on the EDA, it is good. If you are talking about the EDA automation, that is completely a different how methodology we can develop for understanding a chip while we are implementing on the any tool.
Okay.
So I'm able to answer question or
Yes, yes, Rohit. It is absolutely okay. I have another question that you used to talk about the optimization throughout their entire chip designing process. There are various ways of optimization you are talking about. But I was very beginner to this field, so I may ask you that how you usually start optimization. Is there any standard specification or it is given by the customer by yourself with themselves? I am really bit confused.
optimization start from the specification. We have a specification, so we try to the specification every time. And for achieving good specification, we have to optimize in terms of what? Optimize in terms of data. Optimize in terms of what? Optimize in terms of power. If we are saying optimization, so let's see we are using 2 or 3 in our path or any activity. That will also achieve our functionality. If we are using a big cell in place of that 3 buffer, that will also achieve our same functionality. But we have to find which is more suitable for the our design, which is in the specification table. So we do the optimization based on the specification by the customer.
Okay. Okay. Okay, Rohit, actually we have lots of questions because when we have started studying something, so there should be some questions and that is never ending process. But if it is possible for you, we will love to hear from you from for another day also, if you can get some time from your busy schedule. So we are enlightened from your lecture, and I'm asking the others who are present in the platform is if they have any question.
Thank you.
So I think there is no one. If you have any question, you can also put your question in the chat box also. Okay. Okay, Rohit. Again, thank you very much. I think we have come to the end of the session and we can leave. Thank you very much, Rohit.
Thank you.
Okay. Then we are concluding our meeting.